So, привет. As you already heard, я разработчик в KDE. Я не говорю по-русски, мое представление в английском языке. That's kind of it as far as my Russian goes, so I'm going to continue. Usually people, when they see my name, they kind of assume that I'm from around here, but that's not really the case. So for those of you who don't know me, I've been in the C++ community, mainly in the KDE project, for around 10 years. I'm currently finishing a book on functional programming in C++, and I visit conferences a lot to talk mostly about functional programming, sometimes more basic stuff, sometimes a little bit more advanced. Before I start any talk, I usually start with a quote by Phil Wadler. Probably my favorite quote. The idea is you should always write your code so that the next person can read it, because if you can't, then you might your life might be in danger, because usually developers are psychopaths, and the people who work on your code tend to be as well. So this talk is going to be a little bit strange. It's going to be like you want to visit a city, in this case Minsk, but you just use the metro and never go outside. So this will be mostly an overview talk about the evolution of functional programming in C++. We are not going to dive deeper into any of the topics. Some topics will be a little bit more explained, some a little bit less. So when we talk about functional programming, usually we connect a couple of different things to it. The main part of functional programming are higher order functions. Do we all know what higher order functions are? Okay. Then usually we connect algebraic data types, purity, and whatnot. Most often when you ask two functional programmers what functional programming is, you will get three different answers. And most of one answer will be the features that Haskell has, one answer will be what Lisp has and stuff. So the only thing that actually connects all the functional programming languages are the higher order functions. Other stuff is just sugar on top. So as far as C++ is concerned, when did it become a functional programming language? When did we get higher order functions? Any answers? Exactly. So from standardization, so let's say that C++ didn't exist before 98, which is a lie, but let's pretend. It was standardized in 98, and we already had higher order functions. So we had the algorithms. One of the cool examples of how we could use algorithms, if we have a list and the user selected a couple of items from the list, then he uses the mouse to drag and drop to another place. This is something that most of the people would actually implement by hand, writing a for loop, then choosing all the selected items and moving them downwards. Instead, we have a beautiful algorithm called stable partition. If we want to move the selected items to the middle of the list, we can just use the stable partition on the first half of the list to move all non-selected ones to the top, and then move the selected ones to the, unfortunately you don't see the colors very well, right? So the selected ones are 2, 5, and 7, or 2, 5, and 7 on that part. So you get the first part of the list, you do a stable partition, move all the non-selected items to the top. Then you get the second part of the list, stable partition on is selected, and move all the selected items to the top of the second part. And you'll get the selected items grouped in a single spot. And this is quite cool. This is something that people don't usually think about. How can I solve my problem using the STL algorithms? And stable partition is a higher order function. It accepts two iterators, and it accepts a function or a predicate. So we have had this since at least C++ 98. For as long as we had the call operator, we could have created things that look like functions. So let's say that they are functions, although the standard calls them function objects. And we had templates which allowed us to capture anything that looks like a function. So when we talk about functional programming in C++, we usually talk about duck typing. If it quacks and walks like a duck, it's a duck. And in the same way, if it behaves like a function, if you can call it with the call operator, then let's call it a function. So the sad part about C++ 98 was that it wasn't really easy to create function objects. So we had a lot of utility classes in the STL to allow us to create, for example, the function that multiplies two numbers or two integers or whatever. Then we had bind first and a lot of utilities just to allow us to create one-off function objects. Also, we got a few really cool libraries like Boost Phoenix, which allowed us to use a nicer syntax than, for example, std multiplies. We could just write arg1 times arg2, and it automatically creates a function object of two arguments which multiplies said arguments. This kind of evolved in later years. We replaced bind first with bind. We don't need to explicitly state the type for std multiplies. We can just put the diamond at the end. But this is not enough. The moment when functional programming became really a nice thing in C++ was when in C++ 11 we got lambdas. So the main problems were one-off functions. If we don't want to use the same function in multiple places, why would we need to declare it globally just to be used in the stable partition? Then we'll see the problems of STL algorithms and iterators, and obviously a lot of algorithms use tuples or pairs, which kind of sucks, and we will see later why. So we started growing and we got lambdas. Lambdas are just the syntactic sugar to create a function object, which is unnamed, and it's inline. Where we want to use it, we can define it in that place. In this case, we are implementing the negation of the selected predicate. What are we doing? We are creating a lambda that gets any value, and then just negation of predicate of that value. Do I need to explain the forwarding part? Okay, if somebody wants, you can ask at the end. So the problem with the algorithms wasn't that they are not powerful. They're just problematic to compose. Just imagine you have a collection of people, you want to extract all the female people, and then you want to get the names of those females. In STL, it would look a little bit ugly. You would need to combine the erase remove idiom or copy if, and then you would need to use transform to actually get the names. So you have a lot of places where you can make mistakes here. For example, first you need to allocate memory, which is not necessarily needed if you write this by writing a row for loop. You need to create a new vector of names and extract, and you can probably make a lot of mistakes by passing the iterators. For each of the algorithms, we need to pass at least 2 iterators. What happens if we pass an iterate as a beginning, an iterator that comes after the end? We get undefined behavior. What happens if we pass iterators from 2 different collections? We get undefined behavior. That's something that would be much, much nicer if the compiler could catch for us. So instead of using the algorithms, people started investigating some alternative approaches. Instead of getting pairs of iterators, we can create an abstraction called the range, which is essentially similar to a pair of iterators, but a little bit more complex. So it's an iterator and kind of a sentinel. Does everybody know what a sentinel is? So it can be an end iterator. It can be actually the same type as the beginning, but it can be some dummy type that tells us, okay, we are at the end. Again, if you want explanations, we can go back to this slide. And the idea is, instead of all the algorithms getting a pair of iterators, an algorithm can get a range and return a range. And if it returns a range, we can pass it to another algorithm, and so on. So we get something like this. Now, the syntax in this case is a little bit peculiar. It's inspired by Bash Unix shell. So we are using pipes instead of something that would be a little bit more common, like a dot filter, dot transform. But that's the limitation of the language and the library, the range v3 library, and it's not a limitation of the concept. So now look at this code. What does it do? Sorry? So it is some kind of filtration. The problem is that we see and need to work with a lot of code that looks like this, which is something, if you see it for the first time, you actually need to think and to realize what it's doing. It's some kind of filtration. If it's written in the same code with the range syntax, it becomes completely obvious. So at the end, we have the drop and take, which is just, we want offset and count. And then, okay, we want to filter all the components, we just want containers. Then we want to get the children of those containers and then process all the children. This code versus this one. And this is functional programming in a nutshell. This is the first thing that people tend to start loving about functional programming. And at some point I watched a course about the Scala programming language for Java developers. And most of the Java developers, when they saw a code like this, they just went gaga. So they obviously are going to get less salaries because it's much less lines of code. But on the other hand, it's much easier to write than those dozens lines of code they used to write. So the next part is that we fixed the composition part. The next thing in functional programming in C++ is that pairs and tuples are really cool because they can, just like lambdas, are functions that we want to use only once, so we don't want to name them. Pairs and tuples can be used for the same thing. We need a one-time structure. We don't want to name it, we don't want to do anything, it's just a one-time thing. But the problem is that if we want to use the pair, then std sort of the selected part from our becomes selection.first and selection.second. When you read this code, it definitely doesn't communicate that we have a selected range and we want to sort the items in it. Instead, in C++ 17, we got something really cool. Instead of using the pair as a pair, we can just destructure it on assignment. So it will automatically get decomposed into selection begin and selection end. The feature is called structured bindings. You can Google it for the official paper. Now when you see this code, it actually tells you exactly what it does. It sorts from the start of the selection to the end of the selection. You don't have any problems with .first, .second. Now this is obviously not a complete fix. Somebody could have just used the wrong names when destructuring. But at least if you are a developer who sees this code for the first time, you know exactly what it does. So that was the main part about C++ as a as a low-level functional language. So we have higher-order functions, we have ranges, we have everything, but it's not enough. Functional programming is not only here to make your code shorter, it's also here to make your code much safer. So we want to solve a problem. It should be a really simple application. We just need to fetch a web page and to count the words in the page. So it should be fairly trivial. Now, when we see something like this, we can deduce what the states are that our program can be in. So we have the initial state. We haven't yet started counting. We just know the page that we need to download. The second state is, okay, we made a connection to the server. We are fetching the page and we are counting the words. And we have the final state, which is we know the count and we don't care about anything else. And as object-oriented developers, the first thing that we are going to create is a structure or a class that can handle all these states. So, for example, we can have a Boolean that indicates whether we have started. We can have a Boolean flag that indicates whether we have finished. We can have the count, we can have the string and the socket. The problem with this class is that, for example, the count is not needed in the initial state because we haven't still started counting, so what's the point of the variable? The URL is not needed as soon as we connect to the server. And the last, the socket is needed just in the middle state while we are counting. As soon as we stop counting, why do we need to keep the socket alive? So obviously, instead of having two bools, we could have used an enum or something like that, but that's not the main problem in this structure. The main problem is that we are allowing for a lot of invalid states in our program. Now, one place I was a couple of months ago in Akademgorodok near Novosibirsk, and they have the monument to all the mice that were used in the genetical research. And one of the cool things when you think about the DNA, what is a DNA? You have 4 values for one item. Then you have a chain for all of those. So you have almost an infinite space of possible values. The question is how many of them are valid? So in this room we have, let's say, I don't know, 50 different chains. But imagine how many more invalid ones are there. Just imagine what happens when, for example, okay, I'm not going to go into anything completely weird, but imagine after Chernobyl, how many animals were actually born not to be born, because their DNA had just a few bits wrong. Now imagine a random chain of DNA. Would it be ever plausible for it to even be born? So if we just create our types by putting data inside, we are going to allow ourselves to have a lot of invalid states. Instead, we should somehow try to limit those states. So we can think the other way around. Instead of thinking what our class needs to support, we can actually split the states into separate types. So the first state is init_t. It should have the URL, but I forgot to add it. We have the running state, which has the socket and the count, and we have the final state, which just has the count. And we need to allow our program just to have these 3 different states. That's something that's called the sum type. Unlike the previous one, which is a product type when you multiply everything, the sum type can be either A or B, but it cannot be both at the same time. So one way to implement sum types in C++ is by using inheritance. We can create a super type called state T or something, and then all of our subtypes would just, substates would inherit from it. And we would have different classes with a lot of boilerplate because we want to be efficient. We want all the classes to have the static IDs so that we don't need to use the dynamic casting and everything else. But after we deal with all the boilerplate, we can just say our main program is a unique pointer to one of these three. After this, we cannot have an invalid state if you don't allow, obviously, for the pointer to be null. And when we want to handle this state, we can just, for example, when counting has finished, we are asserting that previously we were in the counting state or running t. Then we can use the static cast because we are assuming that we have already been in the counting state if this function has been called. And we can just switch the state to we have finished the counting. Again, this is a little bit tedious because it has a lot of boilerplate, but we cannot have any invalid states in our program, so we can't have any bugs due to the invalid state. What are the characteristics of the inheritance-based subtypes? Again, as said, we cannot have any invalid states. The states can be easily extendable, so you can just add new states if you want without changing the main program. When you switch from one state to another state, automatically all the resources from the previous state get destroyed. Because you had the unique pointer, you make the pointer to point to something else, the previous state is completely destroyed, which is cool. This means that the socket that we have used to access a web page will automatically be closed. But, as I said, the bad point is that it has a lot of boilerplate. As an alternative, again, in the most recent versions of C++ and standard libraries provided by Clang and GCC, I'm not sure about Microsoft, we can do something better. Instead of having a pointer to some of the states, we can just create a proper type-safe union type, which is called std variant. Instead of having inheritance and boilerplate, we can just say, okay, the program state is a variant or a sum type of init t, running t, finished t. We don't need any boilerplate inside of the class states themselves. So init t just has the URL, running t, so we don't have static IDs or anything else. It's all done automatically by the std variant for us. The good thing about the std variant is that it doesn't use any dynamic allocation. It just constructs everything in place. So the size of the variant will be the size of the biggest state that you want to support. When you want to switch from one state to another state, you can just use getif to get to the current state, assert that it's not null pointer, and then you can just say, okay, we formerly had running t as a state, now we have m state equals m finished, and just remember the count. So you don't need to pay attention to any of the pointer stuff. You can't even make the mistake of creating a null program state, which we could in the previous solution. In this case, the only way that you can actually make a mistake is, for example, if some of your destructors for your states can throw and then the variant can be invalid, blah, blah, blah. But our states are really simple and we can't throw in the destructor. So we don't have any boilerplate. We have all the benefits that we had with the inheritance-based some types. The only difference is that here, if we want to change the number of states or add a state, we will need to change the declaration of the std variant, which usually is not a problem, but if you, it can break binary compatibility. So if you want to put something like std variant inside of your ABI, you will need to hide it behind a pimple idiom or something like that. Now, Variants are not really pleasant to use if you want to use them with getif. Getif is a strange function. It accepts a pointer to a variant, then checks first if that pointer was a null, it returns a null. If that wasn't a null and it contains the right type, it will return a pointer to that instance. And if the type was not correct, it will return a null. So it's a little bit complicated. So it's not something that we would actually like to use. There is a function called stdvisit, which accepts a variant and a function that needs to be called on it. If we provide a generic lambda or any other generic function, the stdvisit will be able, whichever the type inside of the variant is currently stored in the variant, it will be able to call that generic function on it. So if you just want to debug and say, I want to print out whatever is currently the program state, you can just say stdvisit generic lambda that prints the value to cout or cerror. The problem is that most of the time we don't really have a single function to invoke on all of the different state types. Depending on the type that we currently have in the program state, we want to be able to execute different functions, but still without the getif. For that, we can use something that might become even the part of STL in C++20. You can create overloaded lambdas. So what is an overloaded lambda? It's a lambda that inherits from a lot of lambdas. Well, it's a function object that inherits from a lot of lambdas and steals the call operator from all of those. So if you want to create an stdvisit construct that can call different functions for different types that we have in the variant, you can just say overloaded and provide lambdas for each of the states. Okay? So if, for example, the m state contains run in t, then this lambda will be called. If you want just to provide two of them and then just say ignore the rest, you can provide two and as the last one pass the generic lambda and do nothing inside. Okay, are there any questions so far? Okay, so apart from normal variants, we also have some special sum types in C++ since recently. The first one is std optional. Std optional is a really cool type which can denote either I have a value or I'm empty. So it's a sum type of nothing and the type t. When can you use std optionals? You can use them to, for example, if you have an API that needs to accept an optional argument. Until now, you would make it a pointer to something and the user would pass null if it doesn't have anything to pass to you. Now you can just say, okay, this argument is std optional of float. If the user wants to pass a float, he will pass the float, otherwise it will just pass the empty optional object. It can also be used if you want to communicate that there was an error. So for example, if you want to implement the square root function, you can decide to return std optional of float. And if you get a negative argument, you just say, okay, there isn't a square root of -1. I'm going to give you the empty optional. Otherwise, I'll give you the optional that contains a value. If you want to use std optional, because we said getif is a little bit, for variants, is a little bit strange. So we can just create a wrapper that instead of using pointers like the normal getif does, we can just create a getif function that returns the optional to something. Obviously, this has a disadvantage that optional values are value types, so this will copy the state. It will not be a reference or anything else. But at least the point of this example is for you to see a function that returns an optional instead of just returning pointers. Another thing that could be quite useful, but is not yet going into standard, although it was proposed, is the problem with optionals when you want to communicate errors is that you just know whether an error has occurred or not. You don't really know what error has happened. So Alexandrescu proposed at some point, this is a well-known idiom from, I don't know, Haskell and other languages, but in C++, I think it was first proposed by Andrei. The idea is, again, instead of we need a sum type that can have a value, and instead of the optional value or not, this has a value or an instance of an error. Andrei proposed that the error should always be an exception pointer, but we could make it a little bit more general. If you want to use error codes, you can use ints, you can use whatever you want, you can use string as the message, as the error type. One question, does anybody want to actually see the implementation of how a type-safe union type can be implemented? Okay. Fortunately enough, that's something that I didn't delete from the slides yesterday. So a type-safe union, obviously you use the C union. So the union will have the size of either T or E, which one is the bigger one. And obviously we need a flag to tell us which of these we actually have inside. When we have all the basics done, if somebody wants to get a value, we can just simply check if it's not valid, we are going to throw an exception or something else. And if we are valid, then we can return m value. The same would go for the function that returns an error. The interesting part of this are the constructors and moves and everything else. So if we want to create a successful or the expected object that contains a value, we need to create an instance of it to initialize m value to be true. And we are going to call the placement new. So instead of allocating a new memory and calling the destructor on that memory, we are going to actually call the destructor directly on pre-allocated memory. Because as I said, our union type has enough memory to store either T or E. But it's not initialized because unions are a C construct and not C++. So what we are doing here, we are saying, call the constructor for T on this memory location. Okay? The destructor is quite trivial. If it's valid, call the destructor for T. If it's not valid, call the destructor for E. And this is boring. Whenever we want to implement things like copy constructors and everything else, they're usually the easy part. The difficult part is always the swap. So whenever we want to implement operator equals, we should use the copy and swap idiom, and the swap is the difficult part. The easy case is when both of the expected values are valid, so we just need to swap the values. The problem arises when one is valid and one is not. And in that case, first we need to steal the error from the other, from the thing that we need to swap with, then destroy it, initialize from our value. We need to call the placement new on the other m value. Then we are going to destroy our value and construct the error in place. And this is something that is really easy to make a mistake. I'm not sure, but I think that even Andrei in his presentation had a slight small bug. So usually you don't want to implement stuff like this. You should download it from from a trusted place on the internet. And in the else branch, if both of them were invalid, just swap the errors. Otherwise, just base our implementation on what we did earlier, just swap the other and start this. Okay? So this is a bit of trickery and something that usually you don't implement, you just use the STL and STD variant does everything for you. So we had a talk by Roman. He had a code that kind of looked like this. We had a handle, we checked the handle. We had another handle, we checked the handle. Just imagine having a lot of optionals. You get a current user. If the user is currently logged in, you get a string. If nobody is logged in, you get an empty optional. Then you want to get the information for that user. You can have the if the user is valid, get information, otherwise ignore. The second, I want to get the name. If the previous one was valid, then get the information, otherwise ignore. And this is something that we do a lot. This is something that C programmers do a lot more than us because we have exceptions, if nothing else. But sometimes the exceptions are not a solution. We sometimes actually need to encode the error inside of the type. For example, if you want to send a type across the network or across multiple processes or something like that. And it would be quite tedious to write code like this one. So instead, we can think of optionals and similar things like containers. So instead of thinking optional is what I said earlier, we can think optional is a vector that can have 0 or 1 item inside. Why don't we use ranges? So if we have an optional, think it's a container, then we pipe it to transform 1, transform 2, transform 3, and how many of these if valid we had. Now there is a problem in this code. What is the problem? Why do you think so? Okay, if you wanted the error message, we would use the expected instead of the optional.
I mean, in that scenario, we have a problem that we need to return and to inform the user what kind of information we requires. And if we return just, we have an error, we don't understand what we need to specify additionally.
I'm not sure whether I understood, but if you mean that if some of the functions fail, we don't have the error.
We don't have understanding what's going wrong.
So if we used the expected instead of the optional, transform would work only on the value part. If the value is not present, but the error message is inside, it will just pass the error message on. So the transformation chain...
Yeah, I mean with optional, not with...
Yeah, of course. That's why I said if we wanted, we could just replace optional with expected of something. And the same thing would be unchanged. So we could also, again, have just transform, transform, transform. But there is a little bit bigger problem here. This is not going to compile for some reason.
We need to apply
so the argument for get info is not optional, but you're right. If we wrote it like this, it would expect it to be. Instead of using transform, if we used it for these functions above, we would get, first we would start with an optional, then we would transform it and get the optional of an optional of something. The next transform optional of an optional of an, and so on. This is a common idiom, and this is something called the monad. So instead of just using transform, we are always going to use transform plus join or flatten. So whenever we get a nested optional, we are going just to extract the optional from it. And if we had the mbind function, which is the monadic transform plus join, this would actually be able to be written like this. And this would work. So whenever we have a chain of transformations that can fail, we can use the monadic bind. As soon as one of the functions fails, we are going to get either an empty optional, or in the case of the expected t, we are going to get the error message. If all of them were successful, we are going to get the final result with all transformations applied, which is kind of neat. Now, this is kind of a little bit just to trigger your interest in monads, but we are going to continue just a little bit. So, what are futures? We all know what a future is, right? So, in a sense, again, futures are containers that can contain a value in some point in future. They usually don't contain it right now, but they will. So why can't we just call transform on a future? Why can't we just call the monadic bind? So again, if we have a lot of asynchronous functions that all return futures, we can just chain them like this. Mbind this, mbind that, etc. As soon as the first future arrives, the result will be passed to the second function, then to the third and fourth, and so on. And in the end, we are going to get the future of the last result. Now, the function that is used for this, for futures, is not really called mbind. It's called the .then. So .then is, it's not really, but it's the same thing as mbind, just with a little bit different signature. But let's pretend that std is actually properly implemented a monad for the futures and not what they actually did. So we would, again, have a chain, and it would all work just as it worked for optionals, expected, and everything else. But the problem with this kind of code is that imperative programmers don't really like it. So we, as smart people in this room who saw the benefits of ranges and the range-based syntax, we obviously love this. But the problem is that most C++ developers wouldn't really love to write code that looks like this. It still looks much better than actually unwrapping all the .thens into something else, but it's a little bit ugly. So what are we going to get in C++ 20? We are going to get the coroutines. Instead of doing the .then, you can just say, okay, auto user equal assign the result of co-await something to it. What does this mean? The current user will return a future. The co-await will check, is that future already here? If it is, the user will get the value from it. If it isn't, then we are going to suspend the current function and continue working on something else until the future arrives. When the future arrives, the user variable will get the value and the function will continue. That's the idea of a coroutine. You can suspend a function and resume it at a later point. And now we can do the co-await 3 times and just continue the code, the normal code afterwards. This should be, in most cases, equivalent to a chain of .thens, but it's easier to read and it will probably be more performant because the co-await is implemented in the compiler itself. It's not a library feature. And this is kind of the breaking point. We can skip over it. So this is a language feature to implement .then. Does it work only on futures though? This is a core language feature that implements monadic bind. So while this in essence was designed to work for STD futures, it can work on any other monad that you can think of. So if you want to use optionals without the bar and bind, you can just say co-await for an optional. If the optional is empty, we are going to return an empty optional. If the optional is here, the auto user variable will get the value. And again, chain. As if any of the operations return an empty optional, our function will return an empty optional. Otherwise, we are going to return a proper value. This is one of the coolest things about the coroutines proposal, because it can be abused for so many cool things. And this will be really, really fast to execute. So, as a summary, I tried to be as quick as possible because we are all tired and I almost fell asleep an hour ago. So we have seen that C++ has higher order functions, and they were present for a long time, but they weren't used because it wasn't really convenient. When they became convenient, we started getting a lot more concepts from the functional world, including some types to implement states correctly. And we can combine all of those in the STD visit to be able to handle STD variants in a nicer way. Then we are getting the monadic design inside of the core language. Otherwise, we could have just used the library features. And that's it. Now, if you want to think about how a compiler works, if you implement something with co-await, it means that you have imperative code based on co-await. It gets compiled through a functional idiom called the monad into something that uses template metaprogramming, which is, again, a functional programming kind of thingy. Everything gets unwrapped into imperative C++. C++ then gets compiled into the internal compiler language, which is functional. It's a single assignment C or something similar to that. And then that language gets compiled to an imperative language called assembly. So it's really, the only reason why I put this slide is for you to think how complex your compiler is. So it goes through a lot of different switches of the paradigm from the imperative, functional, imperative, functional, and then imperative. So whenever you think that C++ compilers are slow, just think of this slide. And that's it. I just want to say thanks to a couple of people. Obviously, Anton for inviting me here, Sergey for getting me in contact with Anton, and other people.
I think now you can ask the speaker.
What happens if you put optional inside a future? Do you need, as a proposal, double core awaits or just single one?
You will need double. So the STD future can denote when the computation has failed. So instead of using STD future of optional of something, you can just use STD future. But if you use both, then you would need the double co-await.
I see. And the second question, how inefficient implementation of then is in current version?
I don't have the problem with the efficiency of it, more with the .then, the monadic bind doesn't, should accept a value and not a future of value. And in the standard, .then accepts the constref, or not constref, it accepts the future of t. So it kind of breaks the monadic design. You can wrap it around and it will work.
I see. Thank you.
One just addition. The co-await, I didn't really try a lot of things in the Clang or whichever compiler supports it. It usually relies on handling just one type of monad inside of co-await. I don't see why it would limit you to use just futures, but I truly hope that co-await future, co-await optional can work. It should.
So the question is about expected. You showed that expected has implementation like manual manipulation of objects and so on. Would it be better to use variant instead of that manual manipulations?
Yeah, the reason why I didn't use variant is just to show how it's implemented. But I agree, if you want to implement your own expected, you should probably declare as a private member std variant of something.
Yes. And second question related to pipelining of my filters and so on. Do they create new containers or it apply in
That's
place?
a great question. Let's blah, 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 blah. Okay, I should have probably remembered.
At the beginning,
Yeah, okay. So as the current ranges proposal goes, all of these, you can think of them as smart iterators. So they don't create collections, they just provide you with views. So for example, if you have a filter, the algorithm, when you actually use the data, it will only then be evaluated. You try to access the first element, the filter, the smart iterator will try to find the first element matching the predicate. So it doesn't create a collection of the results, it just creates a smart iterator that knows how to skip the invalid entries. The same goes for the transform. When you ask for a value, it will just call, okay, the smart iterator get me the first value. It will get through to the original collection and then call the transformation function and return you the result. The result is not stored anywhere until you store it in the end. So in all of these, let's just pretend these two doesn't exist. For 4 different filtered, transform, flatten, and filtered, you have just a single pass over the original collection. And when you add drop and take, you don't even need to pass through the whole original collection. You will exit as soon as you have enough of the items to return. Okay?
Thank you.
So this is implemented quite nicely. When you compile ranges with Clang, you'll get really slow code, but with GCC it should work quite nicely.